This is lesson 6 of the Addre core. In this tutorial, we'll be talking about the receiver state machine. The code for this tutorial can be found at the website projectfpga.com/tcp. Select the receiver state machine. This is the code. This code is what I'll be implementing on Logic Sims for tutorial purposes. So this is what the receiver state machine looks like. These are the different states of the receiver. Starts with the state idle, state drop, state preamble, state SFD, state data. So at the left we can see the inputs which enables the receiver to transition from different states. These are the inputs. Number 1, the IFG counter equals 24. So what does this signal do? So the IFG counter equals 24. IFG stands for the interframe gap. Then the counter equals 24. So in subsequent tutorial, I'm going to show you this counter, IFG counter. So whenever it equals 24, this signal here comes on. So it means that the IFG counter has counted up to 24. That is at a point when it's equal to 24. So what does this 24 symbolize? So the Ethernet standard says that interframe gap, that is the gap between two receiving frames, should be at least 960 nanoseconds for 100 megabits of Ethernet transfer. That is for fast Ethernet, and 9600 nanoseconds for 10 megabits Ethernet transfer. So this 960 nanoseconds is being counted. The counter counts up to 24. It waits up to 24. So 24 counts of this counter equals the 960 nanoseconds. So I'm going to show you this calculation shortly. How when you count to 24, it means that the IFG counter has waited up to 24, has waited up to 960 nanoseconds. So because 960 is the minimum, it has to wait up to 960 before it receives another frame, 960 nanoseconds. So the configuration register, we have to determine if it's going to check for this or not. So there may be situation where there is no interframe gap at all. So all frames are received immediately. One frame has ended, another frame starts reception. But in a situation whereby it is set, that means it has to wait for that 960 nanoseconds. If it doesn't wait, this doesn't come on. So this turns on to tell the receiver that it has actually waited for 960 nanoseconds. So the next signal is MRXD equals D. So let's note that the receiver receives bits in nibbles. Nibbles means 4 bits at a time. Nibbles, 4 bits at a time. So this receiver receives bits nibble by nibble. So when the MRSD is the name of is what we call the received data. So whenever it is equal to D, so let's see, whenever is equal to D in binary means 1101. So it checks, the receiver compares the received nibbles and checks whenever is equal to D. So whenever is equal to D, this signal comes on. Then the next signal, which is the MRSDV, that is MRSD valid. It marks the beginning of reception. So whenever there is a valid data to be received, this MRSDV signal comes on. It tells the receiver that there are data to be received. So it turns on and reminds the receiver, hey, there is data to receive, hurry up. So the next signal, MRSD equals 5. Let's see, 5 and X, it means 010, because since we are receiving in nibbles, it won't be 101, it's going to be 0101. So this bit of data comes on whenever the MRSD is equal to 5, whenever the received bit is equal to 5. So it always checks, it compares the bits and knows whenever is equal to 5 or whenever is equal to D for in this case. So that's that. Then the next signal, transmitting, this shows the valid state. It shows that the carrier is busy. So whenever there is data being transmitted on the carrier, this transmitting signal comes on. Then lastly, the byte count max frame. So in the configurations register, you can set the maximum number of frames to be received per session, per reception session. So whenever this maximum frame is exceeded, this signal comes on. It tells the receiver that, hey, the maximum frame, byte frame to be received has been exceeded. So we're going to see how these different signals influence the state transition, how they influence how the receiver moves from one state to another. So initially, when nothing is on, and then I reset this state machine, it goes straight to the state drop. And after the reset, it goes back to the state idle. So the state idle is the initial state of the receiver. At the state idle, nothing happens. It means that there is no data to be transmitted. That is, MRSDV is off at this point. That is when the receiver turns on. So let's see, this is what makes it 0 and this is what makes it 1. So let's see what signal turns on this state idle. So here it consists of this AND gate here. So this first one says when this MRSDV is not on. So that is when there is no valid data to be transmitted. And so this is a set of OR. It means AND 1. So let's see this first one. So you can see here it's talking about the state drop. Then 2, it's talking about state preamble. Then 3 is talking about state SFD. Then 4 is talking about the state data. So what it's trying to say in essence is if this receiver is in any state whatsoever state, if it's in any of these remaining 4 states and the MRSDV is not valid, that is, there is no data to be transmitted, go to the state idle. So this is how the state idle gets set. This is what sets the state idle. So the next step is when the MRSDV comes on, that is when there is data to be received. So let's see, it goes straight to the state preamble. So whenever there is valid data to be received, it goes straight to the state preamble. So the state preamble is the first state. So let's see what actually turned this state preamble on. So this is when it came to 1. So let's see what turns the state preamble on. It consists of 4 AND gate, that is 4 conditions must be met for it to go to state preamble. So the first one is it must be in state idle. That is the first condition. It must always go from state idle to state preamble. So the next condition, the MRSDV must be valid. MRSDV must be valid. Then these two must not be set. The MRSD equals 5 must not be set. That means it must not have received 5. So once it's transmitting, it's steadily checking that it has not received 010. So long as it has not received 010, it should stay in state preamble. That is, when the received bit is not 010, that means it is still receiving it's still in the state preamble. So that is what it's trying to tell you here. And when the transmitting signal is not on, it should keep receiving. It's going to keep receiving. So let me explain more on this signal MRSD equals 5. So we know that the state preamble from this diagram here, state preamble here usually consists of 7 to 8 bytes of data. So this is it. Usually 7 to 8 bytes of data. So 7 to 8 bytes of data, when it's being sent neighbor by neighbor, is going to be 14 to 16 neighbors. So, and in our case here, the state preamble data is equal to D. That is, for this particular setting we have, is equal to E. So it's going to receive E 14 times. Let's see. There's a decimal. It's going to receive E, the first E, in 14 or 16 times. So this is what we're expecting to receive. So long as it's not equal to 0101, that is, this MRSD equals 5 should not come on, and it should is assumed that it's still in the state preamble. So long as it has not received 5, that is 010, it assumes that this is what it's still receiving, 1110, 1110. So this is what our state preamble looks like, 1110, 1110. So it stays steadily in this state preamble, waiting to receive the next neighbor. So the next neighbor is expecting to receive is 0101. So, and that 0101 is 5. So whenever it receives it, this signal comes on. That is, MRSD is equal to 5. So whenever it comes on, let's see, it goes straight to the state SFD. So you can see from here it has moved from the preamble stage to the SFD. So that is, whenever it receives 5, it's assumed that it has moved, that it has received the SFD. So the SFD here is 0101. So this is the SFD here. So it has now resided in the state SFD. So when it is in this state SFD, so once it has passed this stage, the next stage is the data reception stage. That is when it starts receiving the actual data. So for it to receive the actual data, it has to pass through the interframe gap, must be set. It must wait for that 960 nanoseconds for it to move from this state to the actual data reception state. That is when this interframe gap must be on, then the MRSD equals D, then at this point it has moved to the data reception state. Now can you see the data reception state is the state data. This is the state where it starts receiving data, reception of data occurs. So it's receiving data neighbor by neighbor. you can see that it's switching between state to state, state to state, state to state. It continues like this until this byte count max frame comes on. That is, it has reached the end of data reception. That is when this byte count max frame comes on. So let's see what happens at this stage. It goes back to the state drop. It has received the maximum number of data. It goes to the state. So at this stage, let's look more on what happens at this state drop stage. What is actually this state drop? Because we saw the data move from state idle to state preamble to state SFD to state data. So let's see actually what happens at this state drop stage. So for this state drop to come on, let's see what actually sets it to 1. So this AND gate turns it on. So that means 2 conditions must be set for it to go to state drop stage. So one is that the MRSDV, which is this, must be on. That is, it will only go to the state drop stage when there is valid data. That is, during data reception. So whenever it's not receiving any data and is in state drop, it goes back to this state idle stage. So state drop is more like a suspended stage. It gets suspended at the state drop stage. So until the end of data reception. So at the end of data reception, this MRSDV goes off and it goes back to the state idle. So for it to stay suspended, that is to be in this state drop, the data must still be valid. That is, it must have data to receive. So whenever there's no data to receive, it goes back to the state idle. So is at this state drop, there must be active data for it to receive, and then 3 different conditions must exist for it to stay in the state drop stage. So see the first one here. So this first AND gate says it's when it's transmitting and when it's in the state idle. Okay, that is when there's active transmission and is currently in the state idle and data arrives for it to receive, it should go to state drop. It should not receive the data. So that is what it's trying to say. That is, when it's transmitting, that is when this transmitting is on and is in state idle, that is not receiving anything, that is in its idle state, and then data comes, MRDV becomes set, it should not receive the data. It should go to state drop. That is, it should go to the suspended state. So state drop is the suspended stage, and whenever it goes to this state drop, you should wait there till the end of the data transmission until this MRSDV goes off. So when it goes there, it suspends, it doesn't receive the data, it waits there until that particular data gets received. Then the second condition is here, it has to be in state data. The state data is the data reception stage. That is, if it's receiving data and the byte count max frame comes on, that is when it's in active data reception and the data exceeds the maximum number of frame is allowed to receive, it should suspend, it should go to state drop and discard the rest of the data. So that is what it's trying to say here. That is, it is in state data, it is state data, it is currently receiving data, and this is and this is the byte count max frame. That is, this signal comes on to tell the receiver that, hey, you've exceeded the maximum number of frames you are expected to receive, therefore suspend. It goes to the suspension stage and waits there until this MRSDV is off. That is, until the end of data reception. So at the end of data reception, the MRSDV goes off. Now the third reason for going to the state drop is, 1, when it didn't meet the interframe gap counter. That is, if the interframe gap counter, when it didn't wait up to the required number of waiting time, that is, if it didn't wait up to 960 nanoseconds, and let's see again, and is in state SFD, that is, when it's moving from this state SFD to the state data, it has to wait for that 960 nanoseconds. So now it's saying if it didn't wait for it and is in state SFD, and what again, the last, and this MRSD equals D, it should suspend. It should suspend. That is, if it is in state SFD and it receives D, suspend. So these three conditions, you should suspend until this MRSDV goes off. So let's see. Assuming now is in state drop, let's turn it off and see what happens when we turn it off. It goes back to the state idle. So when it goes back to the state idle, everything starts afresh. So this is all about the receiver state machine. We are going to see how these different states affects the receiver data transmission. Please kindly subscribe to my channel, then go to the site projectfpga.com/tcp and click on receiver state machine to see the verilog code for this state machine I just explained to you now. Thank you.